Now we will see the residuals, which we actually talked about, but we didn't actually give it a name. So when we say yi minus yi hat, when we take that one value, it's actually called a residual. So, and it is nothing, it's just the difference between the actual value here and the observed value. So it's just difference. It's actually error, right? So it's the error. What error is it? It's the error when we use yi hat, to estimate the actual value, which is yi. So it's just the error. It's called a residual. And the sum of squares of these residuals or errors is the quantity that is minimized by the least squares method, as we saw in the last video. So this quantity is actually known as sum of squares due to error. So sum of squares due to error. It's due to error, right? Because we see it's a difference, and difference is the error from the actual value. So it's also called SSE, and it is the sum of squares of error. So like it just follows its name. So it's the sum. That's why we have the summation there. Squares due to error. So this is the error, and there's the square. So that's what it is, sum of squares due to error. And what it tells us is, it basically is a measure of the error in using the estimated regression equation, which is, we've seen it a lot of times now. So when we use that equation to find the values of y, how much the error is going to be, SSE measures that. Now the thing is that we are finding this difference between yi and y naught hat, right? And it's called sum of squares due to error. But what if instead of this value here, yi hat, what if we want to find the difference, the actual value from the mean, right? That can be one thing that can be done. So what if we do that instead of yi hat here? What if we want to find the difference of the actual value from the mean? So that is called total sum of squares, also called SST, and that is the difference of yi from y bar. And what does SST tell us? It basically provides a measure of the error involved in using y bar to estimate sales instead of yi hat. And this was basically all about total sum of squares and sum of squares due to error. But there's another measure, another term called sum of squares due to regression, which we need. Well, we are looking at all these terms, SST, SSR, and SSE, because we will use this later to find R-square values. But what does SSR give us? It is actually a measure of how much the y hat values on the estimated regression line deviate from the mean of y, which is y bar. Well, I think it's just easier if we write it down to see, but this is sum of squares due to regression, and its SSR is equals to yi hat minus y bar square. Well, these all are pretty self-explanatory. Like we can see that SST is a deviation from the bar, from the actual values from y bar. This is the estimated value from y bar, and then this is the actual values from the observed values. So all of these are different terms, and they represent different things which we will need later on. But there is a relationship between these values, SST values. So that relation is that sum of squares, total sum of squares is equals to sum of squares due to regression plus the sum of squares due to error. And this is an important relation. We just need to know this. And using these values of SST, SSR, and SSE, we can find the coefficient of determination. sorry for that fumble there, coefficient of determination, which we all know as r squared, that we have been doing in some of our quizzes, but we don't really know what it is. Well, we sort of know. It tells how good the relation is between x and y. But okay, for r squared, the formula is as sum of squares due to regressions over total sum of squares. So that is how we calculate coefficient of determination. And what does this tell us is it provides a measure of the goodness of fit for the estimated regression equation that we found out using B0 and B1.